So 4.6 will be about modeling with exponential functions. That's just a fancy way of saying we're going to look at problems, word problems specifically, that can be solved using an exponential function. Now, I titled this lesson as Sum Modeling because, quite frankly, it's impossible to go through every single possible application you can come up with. So I'm just going to talk about a select handful. This is definitely not the end-all be-all, and you may come across different situations or contexts that involve exponential functions, but at the very least, we'll talk about a handful today. So actually, we've already done something with exponential functions. Recall, we've already talked about continuously compound interest, right? Continuously compound interest. So we've already seen exponential function work within the context of money. It was A equals P, E raised to the RT power. And each of these letters stood for something, right? A was the final amount, P was the principal, that was the initial amount, R was the interest rate as a decimal, and T was the time in years. And we used this formula whenever the number of compounds was continuous. So remember that the idea of compounding interest is applying the interest, applying a change to your amount. Now, typically with money, we apply change at discrete intervals, once every month, once every week, so on and so forth. But on the off chance you wanted to sort of ramp up the amount of change, or like maximize the amount of money you can have, you do this thing called continuously compound. That's sort of like changing the amount of money every split second, every nanosecond, every waking moment in life, like constantly changing. That's where the word continuously comes from. Well, it turns out that there are a lot of things in life, in the universe, that are constantly changing. Hair growth, our heights, cellular growth, population. So not surprisingly, that a lot of things in nature, biology, sort of follow exponential models. Now, here's the cool thing. It follows this format, right? A equals P, E raised to the RT power. The only difference is the letters simply change, the meaning changes depending on the context. If we're talking about money, the formula becomes APERT. Well, what if we're talking about like life, biology, population? So let's take a look at one model here. Let's take a look at exponential population growth. So let's compare this model with what we already know, continuously compound interest. This model states that the number of a particular population is equal to the initial population times E raised to the relative growth rate times time. Now, isn't this basically the same formula? The final amount, the final number, equals the principal, the initial amount, the initial number, E raised to some rate times time. So it really is the same formula, guys. It's just you change the letters depending on the context of your story or of your problem. So let's go ahead and define all these variable means, where n of t is the population at time t, n sub naught is the initial population, r is the relative growth rate. Come on, scroll up. There we go. And t is the time in whatever units r is in. Right? So if your growth rate is every hour, t will be the number of hours. If your growth rate is per year, t will be in years, so on and so forth. Right? But I hope it's like it shouldn't be a new formula. If you understand how continuously compound interest works, if you understand how E sort of changes the interest formula into this sort of new compound interest formula, you'll find out that every single model follows this exact format. It's always some initial amount times E raised to the RT power. You're just changing the letters, changing the context depending on the story. So let's do a couple of quick examples here. I guess I shouldn't slash this. It'll be part of the same group. Let's do an example here. Now, I hate to say this. It's going to be a lot of writing. All of our examples will be word problems. Suppose an initial bacterium culture starts at a count of 500. Basically, we have some bacteria here and there are 500 cells. A biologist later makes a sample count of bacteria and finds that its relative growth rate is 40% per hour. So this biologist checks in on the sample later, does another count, and calculated that it seems to be growing 40% of its current population every hour. After how many hours will the bacteria count reach 80,000? So let's go ahead and do this. Now, the first thing I would do is analyze what type of problem we're doing. Clearly, it's about growth. Heck, even uses the specific word growth right here. So we know it's about exponential growth. Now, the first thing we would do is build a model. So because I know it's exponential growth, I'm just going to write down the default model. And then all I'm going to do is figure out what information they gave us and figure out what information we're trying to solve for. So let's highlight in yellow what they gave us. Well, here it says it starts at a count of 500. I hope everyone agrees. That's clearly the initial amount. Actually, I'm not going to use yellow. I'm going to use various colors here. A biologist later makes a sample count of bacteria and finds that its relative growth rate is 40% per hour. So that's pretty obvious. 40%, that has to be the rate. After how many hours? So that's the actual question. After how many hours? After how many hours? That's time. How many hours? That's the number of hours. That's time. Will the bacteria count reach 80,000? So this should be the final amount, and that's where we put it. So these problems, it's basically just reading and putting the numbers in the right spots. It shouldn't be too difficult if you're okay with parsing information. So that's it. That's the big secret. Just plug everything in and solve. There's really not much more to that. It's very anticlimactic. So 500, E, the blue was 40%. And as with our compound interest, the percentage should always be a decimal. And time, that's exactly what we're looking for. So I'll leave it as a variable. So notice this is an exponential equation. The variable that I'm solving for is in the exponent, so it's an exponential equation. We just did this. I think this is 4.5. So solve for t. The first thing I want to do is get the exponential by itself. So let's get rid of the 500 by dividing both sides by 500. Now that the exponential is by itself, I can go ahead and use a log. We'll go ahead and use an ln here. So I'll do an ln on both sides. Here, the ln and e cancels out. Gives us ln of 160 equals 0.4t. And then the last step is to divide out that 0.4. So t equals ln of 160 over 0.4. Now, when it comes to word problems, I actually don't like exact answers. So go ahead and approximate it. So that's about 12.69. Now, remember that your t will always be in whatever units your r is in. So in this case, since our growth rate was 40% per hour, these t values represents hours. So if you leave this bacterium alone for about 12.7 hours, it's going to go from 500 to 80,000 bacteria. They grow fast. Now, the one thing you have to bear in mind, you can only use this exponential model if you have a relative growth rate. That is to say, a percentage growth rate, a rate that relates to the current amount. Oftentimes, though, biologists, naturalists, people who study population, they don't get that. They don't get that information. Rather, they have doubling time, tripling time. They notice, oh, the population doubled in this amount of time, the population tripled or halved in this amount of time. Well, we have to convert that into a relative growth rate. How do we do that? Well, let's take a look at this next example. Suppose a culture starts with 10,000 bacteria, and let's say the scientist, whatever, just his only job is to stare and count the number of bacteria, and and the scientist observes that the number doubles every 40 minutes. And let's say I want to find a formula that models the situation, right? Find a function n of t equals n sub naught e to the rt power in that particular format that models the number of bacteria after t hours. So the first thing I'm going to do is just parse the information, right? So we have culture starts, 10,000 bacteria, so that's very easy. That's the initial amount. And we have the number doubles. So I hope everyone agrees that when you double something, you're timesing it by 2. Now here's the key thing about this problem. It's trying to be sneaky here. It tells us it doubles every 40 minutes, but the question wants t hours. So just keep in mind that you're going to have to convert the 40 minutes into hours. So I guess I'll keep that in pink. So note 40 minutes is 2/3 of an hour, right? 40 divided by 60 is 2/3. So let's go ahead and, answer this question here. So just plug everything we know. So we have n of t equals n sub naught, that's the initial amount, so that's 10,000, e to the r power. They didn't give us an r, so that's a variable. They give us a time, that's 2/3 of an hour. The only thing I'm missing is this guy here, right? I need a final amount. And now, at first blush, it looks like they didn't give us a final amount. They didn't say, hey, you ended up with this amount. But remember, this guy here in gray, we know he doubles. Well, if I know it starts with 10,000, what number would be double of 10,000? 20,000. So we should know at 2/3 hour, aka 40 minutes, I know for a fact that the population is at 20,000. So although it didn't flat out tell you, we sort of have to have the wherewithal to know that, oh yeah, final population is 20,000. It's double to what I started with. So I hate to say it, we actually have to do a little bit of thinking. We have to use our brains sometimes in mathematics. Then it's an exponential equation, solving for r, yada, yada, yada. Hopefully this should be like automatic by now. So the first thing to do is get the exponential by itself. So let's divide out 10,000. Then I'm going to take the ln of both sides, multiply both sides by 3/2, and there we go. Just there is your relative growth rate. So I'm going to just pop that guy into the calculator because I sort of want a decimal. So R is roughly 1.0397. Now, it didn't say find the rate. It said find the complete formula, right? Find a function. So once you have the rate, all you got to do is plug it back into the exponential growth function. Now, when you're building a model, the only thing that should be variables is n of t and time. Your initial amount and your r should always be filled in. So there is our final equation. N of t equals 10,000 e to the rate that we found out times time. So just like when we did compound interest formula, when it comes to population growth, all it is just using the right model, which is not a new model we need to memorize. It's the continuously compound interest formula with different letters. Plug in the information they give you, solve for what's missing. Right. What other contexts, what other word problem situations can we use exponential functions for? Well, we can do the exact opposite. We use exponential models when things grow. Not surprisingly, we use exponential models when things decay. One very, very common application is radioactive material, radioactive decay. So let's write down the model. Radioactive decay can be modeled by m of t equals m sub naught e to the negative RT power. Not surprisingly, it looks almost identical to all the models we've been using, with the exception of I use m for mass instead of n for number. And notice that the exponent is negative. Well, it has to be negative because we want to do a decay model. All right, let's define all these pieces are. M of t is the mass of the element of the substance after t time. M sub naught is the initial mass. R is the decay rate, and T is the time. And as before, it's the same units as the R, be it days, weeks, years, months, seconds, so on and so forth. There's one extra piece of information that we should know when it comes to radioactive decay. There's actually a straightforward direct formula to find out what R is. When in the previous examples, we actually had to plug stuff in, work with the equations to solve for R. There is a one-stop shop formula to figure out what R is. In this particular instance, radioactive decay, R is always ln of 2 over h, where h is the half-life of a substance. In chemistry, half-life is, by definition, the time it takes for a substance to lose half of its amount. So h is actually a time value. Let's dive right into a few examples here. Suppose polonium-210, that's 210PO in the chemistry symbol, has a half-life of 140 days. Suppose a sample of this substance has a mass of, let's say 300 milligrams. It's a multi-part question. Find a function m of t equals m sub naught e to the negative RT power that models the mass after t days. All right, so just as before, you just plug everything in. Your final answer, however, should have m sub naught filled in and r filled in. So everything else should stay as a variable. Well, we got half of the formula for us. They tell us that we start with 300 milligrams. Now, all I need to do is figure out what R is. Now, fortunately, with radioactive decay, remember, we do have a one-stop shop to figure out what R is. R is always going to be the ln of 2 over the half-life. Did they give us the half-life? You bet they did. So just plug it in. I mean, that's, like I said, these problems will be very anticlimactic if you know the model. Just plug stuff in and there you go. So immediately we can figure out what R is, ln of 2 over 140, which is about 0.005. Right. So there you go. We're done. There's our model. Our model is m of t equals, we started with 300, e to the negative 0.005 t. The negative is always a part of the problem. Oops. Come on. There we go. The second part of the question, find the mass after 1 year. Right. Now, this should be easy, right? Once you have the model, which we did in part A, it's just plug and chug. But be very careful. If they're going to trick you, I'm not saying they will, but if they will, it will be when it comes time to using the formula, using the model, plugging stuff in. Remember that the time t will always match the units of your R. In this case, R relates with half-life. The half-life was in days. The question is asking for years. So a common mistake people would make is they plug in a 1. We do have to remember that 1 year equals 365 days. And we are forced. We have to use the number of days because we built this R value by using days. So that's all. That's the only extra thing you need to remember for part B. We're plugging in 365 rather than 1. The right-hand side is all numbers, so you just take out a calculator, pop them in. That's going to be about 48.37 milligrams. So there you go. Exponential applications. You can do growth stuff, usually with population, bacteria, rabbits, human beings, that sort of stuff. Or decay situations, which will almost always be radioactive decay in our class here. The last application of exponential models is something called Newton's law of cooling. And it's actually a pretty cool idea. Scientists, researchers have actually found a mathematical model to predict the temperature of an object that's just, sitting on the countertop cooling off. So if you have 5 hours to spare and you're wondering what to do, boil up some water, take its temperature, leave it out on the table, and come back and take its temperature, and you can find out that these equations are pretty gosh darn close. So let's go ahead and write down what the model is. If T sub naught is the initial temperature of an object, T sub S is the surrounding temperature. That's sort of like the ambient temperature, the temperature of the room, that sort of stuff. Then the temperature, if I can spell, of the object at time t is modeled by the following function. T of little t is equal to t object minus t surroundings times e raised to the negative r, or negative kt, plus t surroundings. where k is a constant that depends on the object. So instead of talking about rates, we're talking about constants. It's just a physical attribute of the object. So if we're talking about water or coffee or, I don't know, a turkey that you're baking in the oven, that K value will change depending on the material. And these problems will almost always involve you solving for that K value. But notice it's just a regular exponential function. It's sort of different than our compounded continuously formula, but it basically has the same skeleton. You have some amount times e raised to some exponent times t. We just have this extra t sub s here because that's sort of like the starting point. That's the asymptote. You know that when you leave an object to cool to room temperature, it'll never ever get colder than room temperature. So that's why we need the horizontal asymptote to be the surrounding temperature. So that's why there's a shift upwards. But to use it, again, is like always, just read what the information tells you and plug stuff in. All right. Suppose, for example, a cup of coffee has a temperature of 200 degrees Fahrenheit and is placed in a room that has a temperature of 70 degrees Fahrenheit. After 10 minutes, the temperature of the coffee is 150 degrees Fahrenheit. Find the function that models the temperature of the coffee. So our final answer should be a complete formula. And again, just like before, if your complete formula, complete model, should only have variables t of t and the little t. Everything else we need to sort of like put numbers in. So let's go ahead and do this. So the first thing we need to do is just figure out what information they give us. A cup of coffee, I'm going to start reading from the beginning. A cup of coffee have a temperature of 200 degrees Fahrenheit. So that's clearly the temperature of the object. And is in place in a room that has a temperature of 70 degrees Fahrenheit. So that's clearly the temperature of the surroundings. After 10 minutes, so that's T here, the temperature of the coffee is 150 degrees Fahrenheit. So that's the final temperature. So that's T of T, or technically T of 10 here. Find the function. Okay, so there we go. Just start plugging stuff in. So T of 10 is 150. Let's just go ahead and write down the model here. So that's T object minus T surroundings, e to negative kt plus t surroundings. So let's just plug everything in. They tell us T of 10 is 150. The T of the object is 200 minus surroundings is 70. E to negative k 10 minutes plus the surroundings is 70. There we go. So all you got to do is solve for k. So subtract the 70. Divide out the 130. It's not going to be perfect, so I'm going to leave it as a fraction. Take the ln of both sides. And then divide out the negative 10. So k equals ln 8/13 over negative 10. Pop that guy into your calculator and you get about 0.049. There we go. We're done. You just got to plug everything back into your final model. Remember, if they ever ask you to come up with a model, your output should always be a variable and your independent variable should always be a variable. Everything else should be should be numbers. So if T of T equals 130, that's what we had before. Yep, see, 130, that's what we had before. E raised the negative k value, which we just solved for, 0.049 T plus the surrounding temperature, 7. This model here will guarantee you the temperature of the coffee at any given time. So if you want to try this out on your own, get a cup of coffee that has at a temperature of 200 degrees, go into a room that's 70 degrees, just let it sit there for however many minutes you want, and then this formula will predict its temperature. So there you go. It's a nice way to kill a couple of hours on the weekend. So that's modeling using exponential functions. There are a bajillion different types of applications. It's impossible to go through all of them, but at the very least, we should be comfortable with 3 contextual situations: population growth, radioactive decay, and objects cooling to room temperature. Have at it. That is 4.6.